Hello and welcome back to another Physics 2212 video. I'm Colson Cunningham. This is Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab is to showcase knowledge of physics principles, to investigate the distance dependence of a magnetic field, to implement the Biot-Savart law, to approximate the magnetic field from a bar magnet, and then to compare that measured field with the simulated magnetic fields on Big Python. The principles at stake here are the Biot-Savart law, which essentially describes the magnetic field at a given point in space as the sum of tiny magnetic field contributions from throughout the magnet. And we're going to be using several of these equations to calculate the magnetic dipole moment, which is this mu, and we're going to equate that to this equation, which is this constant is equivalent to the sum of all the different dipoles throughout the magnet, as well as the linearization and superposition of magnetic fields. The superposition allows us to compensate for the magnetic field of Earth, and linearization allows us to extrapolate from our data this k and n constant. Findings are that as you get farther away from the bar magnet, the magnetic field decreases, which means that magnetic field and distance are inversely proportional. Magnetic dipole is 3.22, and the measured magnetic field was 55.15 microteslas, simulated was 48.53 microteslas. The system in this lab is the observation location, which is the magnometer or my phone. Surroundings being the bar magnet, which is acting upon my phone. Here is the bar magnet with our magnetic dipole moment and the magnetic field going around the magnet. Procedure: we're using a bar magnet, meter stick, physics toolbox, magnometer, and some tape to determine where the magnometer is within my phone, and then to compensate for magnetic north and measure the on-axis and off-axis magnetic fields by measuring the distance from a preset field strength that we're looking for, which was 20, 50, 70, 120, 170 Teslas. And then measure the distance for the 100 Tesla field, and then record the y component of Earth's field, follow the distance, move the magnometer, and repeat in order to find the off-axis magnetic field. Here's the data I gathered. We have our distance and the magnetic field at those distances. And then from there we took the average and used that to create this plot here, which is the natural log of these values. And we used the linearization of this data to find our n and k values. And then here's the data for the off-axis field. As I had mentioned, we're going to set these two equations equal to each other and solve for mu, which is the magnetic dipole moment. Using our linearization from the data, we found n and k. Plugging that into mu, we get 3.22 for our magnetic dipole moment. So when the magnometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as it gets closer to the magnet, the x component of the magnetic field increases, which continues to emphasize the inverse dependence of distance and magnetic field. Here is the code I set up through VPython. We have our constants up front and distances measured throughout our experiment, as well as drawing the magnet and finding the mu hat and magnetic mu. Here is finding the magnetic field, and function for finding the magnetic field, drawing arrows and determining our locations. I got lazy here, so I did a for loop to solve that for me. And then the last bit of my code is mainly just printing out our different values, the command window, but also just calculating the magnetic field at 45-degree rotation. And here's the result. You can see bar magnet, our on-axis and off-axis magnetic fields, and the magnitude at 45-degree rotation. So, as mentioned previously, magnetic dipole moment was 2.22, experimental and simulated. The magnetic fields are here with a 13.64% error margin, likely due to human error, but also imprecision of measuring instruments and impact from other magnetic fields such as other devices and other pieces nearby. So if I hadn't oriented my experiment to compensate for magnetic north, then the measured magnetic field would be different. X component magnetic north would contribute to the field measurement. Y component would change due to not accounting for magnetic north, and Z component would be unaffected. And the magnetic field would approximately double, and the distance for each magnetic field would decrease due to increased magnetic field magnitude for both magnets. Thank you very much for watching.